Hello and welcome to podcast number 3 with the topic being antibody structure and what antibodies do for us. So probably everybody's heard of an antibody before, like you have antibodies to infections in your body. Antibodies are also called immunoglobulins. So if you see immunoglobulins or antibodies, it's the same thing. If you look on the right-hand side, you see the cartoon of an antibody. So let's look from inward to outward. So there's two heavy chains, and you can see they're red and peach colored. So you have each heavy chain is red and peach colored. And then you have two light chains, which are also red colored and then peach colored at their tips. And you can see that the two heavy chains are held together by disulfide bonds. Those are S for sulfur. And then also the light chain and the heavy chain is held together by a disulfide bond. And you can see it's in the shape of a Y. So the Y part of the antibody is called the arm, and then the stem part of the antibody, or the Y, is the stem, called the stem. And then you can see that the Y, the arms of the Y could potentially move, so that's where that movement could take place. That's called the hinge region. And then if we look at both the heavy chains and light chains, you can see that there's a constant region, that's in red, and then there's a variable region of the heavy and a variable region of the light chain, that's in peach. And then you can see that's where the antigen binds. So, but more specifically, if you listen to the podcast on antigens, that's where the epitopes on the antigens will bind to the antibody, is in this variable region. So the variable region then is made up of a heavy chain and a light chain component. And then if we look at what the text says, it says antibodies are similar to B-cell receptors. That's BCRs. Antibodies are similar to B-cell receptors, but they lack the transmembrane portion of B-cell receptors. So remember, B cells and T cells are the major cells of adaptive immunity, and I told you that they recognize specific antigens and epitopes with their B cell receptors, and then T cells recognize specific epitopes with their T cell receptors. With B cell receptors, they're shaped, the B cell receptor is shaped just like the antibody that B cell would secrete, and the stem part of the B cell receptor would be embedded in the plasma membrane of the B cell. And we've got another podcast on B cells specifically. The arms of the antibody are also called Fab regions, and then the antibody stem is also called the FC region. So what do antibodies do for us? One thing they can do is they can activate complement. So we've talked a little bit about the complement cascade when we talked about innate immunity. So if you look at the antibody, what happens is in the specific immune system. So let me back up for a second. Complement, the complement cascade can be active in both innate and adaptive immunity. So, but we are in adaptive immunity now. So, what I'll tell you is, when an antibody specifically binds an antigen and an epitope on a pathogen, that antibody now is lodged or is stuck to that pathogen that has invaded your body, and now complement proteins, remember they're floating freely in your blood, those complement proteins then can bind to the complement region on the stem portion of the antibody, and then through a series of enzymatic events and cascades, molecular cascades, then the complement system becomes activated, and activation of the complement system leads to inflammation. And inflammation we talked about with nonspecific immunity, but inflammatory mediators can eventually go on to destroy the pathogen. The second thing that antibodies can do for us is if the variable region of the antibody recognizes that specific antigen and epitope, then if that toxin or that bacteria or that virus gets coated with antibodies, then that bacteria or virus can't function anymore. So even though the antibody hasn't destroyed the foreign invader can't perform its function, which is basically to kill you. So here's a cartoon of neutralization. So you can see the bacterium or the virus or the toxin is coated with antibodies. And the antibodies in this cartoon are recognizing adhesin proteins on the bacteria and the virus. The third function of antibodies is to act as opsonins in the process of opsonization. And if you are an antibody and you find that specific antigen and epitope on the foreign invader and you bind to it, what that does is that makes the bacteria or the virus more seductive and more likely for a phagocyte to come and phagocytose the coated or the opsonized microbe. So you can, in the cartoon at the bottom, you can see there's a bacterium and an antibody is bound to the antigen epitope site, and in the phagocyte, so it shows the pseudopod of the phagocyte. The pseudopod of the phagocyte has an FC receptor protein in its plasma membrane that will recognize that stem of the antibody, and now the phagocyte can phagocytose the foreign invader. That's opsonization. And then on the right-hand side, it just shows a more detailed cartoon of a pathogen with its antigens and epitopes, the red triangles, being opsonized by an antibody. And then remember, the FC region of the antibody will bind to an FC receptor protein on the phagocyte, and then phagocytosis will ensue. Antibodies can also bind to the foreign invader and stimulate production of hydrogen peroxide and other oxidants by specifically neutrophils. And hydrogen peroxide, of course, will kill bacterial cells. The fifth antibody function is called agglutination. So if you look at the bottom of the cartoon, you see antibodies binding to the bacteria and then forming a big agglutinated complex. And if you took 202 and you saw that if you had a mismatched blood transfusion, agglutination of antigens and antibodies would occur, cause a blood clot. And then the sixth antibody function is antibody-dependent cellular toxicity. So if you look at the cartoon on the bottom right side, you see the bacteria and the antibodies binding to the bacteria, and then an NK, a natural killer lymphocyte, can come and bind to that FC portion of the antibody via its FC receptor protein, and then the natural killer lymphocyte can release perforins. Those are protein molecules that can basically punch holes in the bacteria and cause the bacteria to lyse and